Our next speaker is Evan Sparks. He is a third-year grad student in the AMP Lab. He has done a lot of cool work with ML-Base, ML-Lib, and he's going to be talking about machine learning pipelines today. And this is also one of the things that you'll be doing in your hands-on exercises later this afternoon.
Sorry, All right, good. Welcome, everyone. My name is Evan Sparks. Thanks for the introduction to me. I'm a third-year grad student here at the AMP Lab. And today I'm going to talk to you about machine learning pipelines. So this is joint work with Shivram Venkataraman, Tomer Kaftan, Gylfi Gunmundsson, Mike Franklin, Ben Recht, and a few others who've contributed along the way. So I'm going to start the talk by asking a kind of a simple question, and that is, what is machine learning? You've heard about it a lot today, and it's kind of a question that's sort of in the air. And so whenever I have a question like this, I ask the internet. So Wikipedia tells me this long definition, and I'm not going to read it to you. But the essence of this thing is that machine learning is a study of algorithms that learn from data, and they produce this thing called a model, which from looking at this data, and this model can make predictions or decisions about your data rather than following some explicitly programmed instructions. And so this is sort of the definition that we all think about, hopefully, when we think about machine learning. Moving from sort of rule-based systems and imperative programming, if statements and whatever, to things where the machine makes decisions for us based on data. So right next to this definition, there's this picture of machine learning, and it looks like this. And that's like, I don't know, that doesn't seem like that definition to me, but hold on for a second. So, I have some data, and that in this case is some points in space. There are these little circles, and they're in this, sort of X and Y, X1 and X2 dimension, and they're black or white. And we want to learn a model, this line that separates these points in this space. Okay, so that's sort of the textbook definition of machine learning. And in this case, our model is, an SVM, because that's hinge loss, and there are a bunch of different models we can choose from. So what are some ML problems that arise when we go to apply this stuff to real data? So the first is that our real data often is not in this sort of beautiful d-dimensional space of real numbers. The input to an SVM might look like this, but real data often looks like this. It's pictures, of airplanes or automobiles, along with labels. And this is like a really nice, machine learning problem. If you tell me I've got to match pictures to labels, that's like as well specified as they get. So real data is sometimes not well behaved according to my algorithm. So even if I take, these pictures and convert them into pixel values and feed them to my SVM, it might not work well. So instead, I need to do something called feature engineering or feature extraction. So I need to find a way of describing these images in a way that is amenable to use in my machine learning model. And then I might even need to apply some sort of transformations to that data, even after the features have been engineered, in order to make the input sort of well behaved according to my algorithm. So finally, this stuff almost never works in one shot, and we've got to do some hyperparameter tuning. That is, we've got to try different model families. We've got to try different settings of those model families. Maybe switch from SVM to decision trees. Maybe we, change the learning rate or the regularization parameter. And so this is sort of an iterative process. So that's the ML side of things. What are the systems challenges here? So of course, we're living in the era of big data. Our data sets are really big. One possible solution to this problem is to start thinking about using distributed computing to solve these problems. So distributed computing, as easy as we're trying to make it here in the AMP Lab, it's still fundamentally a hard thing to do. It's way harder. The paradigm shifts from doing sort of single node computation. And then third, this is sort of at the crux of machine learning meets systems. It might be sort of that a lot of these machine learning algorithms that work well on sort of single node, scaling them up to lots of nodes, lots of computers doing this computation at once might be just fundamentally really hard. So as a quick example, if you search for NIPS papers that have the word scalable in them, this is one machine learning conference, has over 350 papers on scalable methods for machine learning. That's crazy, right? This is like some of the smartest people in the world at one conference talking about how we take these things and make them scalable. So it's tricky. And so the goal of the ML-based project is to make distributed machine learning easy. Easy for developers of new algorithms to take these algorithms and apply them at scale, and easy for end users to take these algorithms and use them. And so, you've seen MLlib in the past, hopefully, or you saw it yesterday. And so that's sort of a first cut at this effort, but there's still a long way to go. So for the rest of the day, I'm going to talk about pipelines. So what do we mean when we talk about a machine learning pipeline? A standard pipeline, if you look at the textbook, looks kind of like this. And I'm a systems guy, so I like box and pointers diagrams, but math equations might fit here as well. But anyway, so we start with our data, we train some classifier on that data, and we get a model. And that's all there is to it, right? Well, no, I've already told you there's this extra step called feature engineering, feature extraction. Then I have to, pick a model that I want to actually train on. So in this case, in this example, I'm using linear classifier. It could be SVM, it could be anything else. And then finally, I get a model out. But the work doesn't stop there. There's actually this other thing about deploying my model. And you heard about Velox a little bit this morning. That sort of gets at the problems associated with this effort. But basically, the point here is that my machine learning doesn't stop at model training. We actually have to use the models. We have to evaluate them on test data to decide if they're any good. And we want to be able to use these things to actually make predictions in the real world. So what does a real machine learning pipeline look like? Well, it starts to look more like this. So all of a sudden, and this is, by the way, a real pipeline from Adam Coates and Andrew Ng, just from a couple years ago. This is for image classification. And so it starts to look a lot more complicated, right? There are a lot more boxes than that, data, feature extraction, model, et cetera. But if you squint and you look real hard, these boxes sort of make up feature extractor. Feature extractor, is composed of 5 of these things, and you don't have to worry about what these things are just yet. I'll get to that in a minute. But basically, my data has to go through several stages of transformation before it's ready to be used by my model. And then at test time, I have to be very sure that I apply the same sort of feature extraction to my data before I feed it into my model. Otherwise, the model will make crummy predictions. So this step of taking this box of feature extractor and squeezing it into a thing that I apply to my test data is crucially important to deploying these things in the real world. So here's a simple example of what it looks like to encode a pipeline like I just showed you in our API. So this is 20 lines of Scala code. This is not exactly the same pipeline, but it's a very similar one. And what am I doing here? So I'm going to load up some images, and then I'm going to apply some normalization. I'm going to do some featureization. I might apply some nonlinear transformation. Ben Recht has this really cute trick about taking kernel SVMs and turning them into linear SVMs with the right featureization. And I do some noise reduction and so on. The point is, though, that each of these individual sort of boxes is a thing that I can reason about and think about sort of on its own, and then I can compose these. So this is kind of, we're talking about composing these pipelines out of simple sort of ingredients. And again, I want to stress that this is sort of the whole thing. As long as you've got your data loaded in Spark, you can just apply this to it, and you get both training error and test error. So what is the sort of secret sauce that makes this so simple? Well, it's sort of deceptively like, a simple idea. And so what we said is this is sort of the core of the pipelines APO, and it's just like embarrassingly small. And what we said is, okay, pipelines are these things that they're made of nodes. So these are, data transformers. And nodes have to fit together in a way that makes sense. So nodes are really just functions that have some input type and some output type. And when I say they have to fit together in a way that makes sense, the output of the first node has to be the same type as the input of the second node in order for you to actually compose these things and even compile them. And that's kind of important. Because as you saw a few slides ago, these things get very complicated very quickly. But then you start to think, well, pipelines if they're composed of functions that are composed together, maybe they are just functions and they are just nodes. And so you start to be able to reuse components that you build out of smaller components very quickly. And then the last thing, this being the AMP lab and our focus on sort of large distributed scalable things, the individual components themselves should be things that we know how to scale. So they, where possible, should be sort of horizontally scalable, something that I can apply a map on and do individually on all my data items. And then there are going to be things that, like optimization routines and so on that require communication sort of across the cluster, but we should be very disciplined about how we write those things so that we don't end up with a system that sort of falls to its knees when you throw a few terabytes at it. And so, that idea of building, composing these systems, these complex pipelines out of components that we know to scale leads to, full pipelines that scale. So, I showed you the API, and that's pretty simple. And so obviously we've had to build a bunch of cool stuff on top of this, and we've been able to. And so we have some example nodes in a few different application domains, so images and text, as well as we've got speech coming soon. But basically, these are sort of domain-specific data transformers and extractors that get your data into a form that then you can throw at these machine learning models and other statistical pre-processing tools. So in addition to the domain-specific tools, there's a bunch of general-purpose tools, things like PCA and fast Fourier transforms are very useful in sort of signal processing, and things like QR decomposition are just sort of generally useful for large-scale linear algebra and supporting a lot of these models. So along the way, as part of this project, we built this ML matrix thing, which is distributed linear algebra on Spark, and that's a component that we're reusing all over the place. So in addition to the individual nodes, we've also got a bunch of example pipelines end-to-end in each of these problem domains that show how you go from images to something that classifies images, how you go from voice audio to something that does sort of speech-to-text translation. And finally, in the text processing domain, we're working on event argument extraction and text classification. And so those won't be in the repository you're using today, but they'll be coming soon from the lab. And so on top of this, we've talked about this in the past. We're doing some hyperparameter tuning work. So actually, making the machine think about how to assemble these things for you. I won't be talking about that today, but you can stay tuned. There's some work under submission there as well. So sort of back to our real pipeline here. So this is, again, like I said, a real pipeline for image classification. And I told you not to worry about the boxes, and this seems crazy, but you're going to build this today. You're actually going to build and run this thing, on your laptop on sort of a decent-sized data set of 60,000 images. And that sounds crazy, right? So I ask you to bear with me for a minute. And we're going to go back, and we're going to have a computer vision crash course. So I want to preface this by saying I'm not a computer vision expert by any stretch of the imagination. I had never done anything with computer vision up until this year. But if I can learn it, I kind of hope that you guys can too. But I'll apologize to the esteemed Berkeley vision faculty for any mistakes I might make in the next few minutes. So anyway, computer vision, what am I trying to do? Again, we're back to this example. I'm trying to classify images as to what's in them, okay? So the simple and naive thing to do, as I sort of alluded to earlier, is to take my RGB pixel values and just represent them as numbers. So I've got an image, it's 32 by 32, it's got 3 channels, that's a few thousand numbers, and they're all in 0 to 255, and what do? I take that and I throw it through an SVM, and I get back a model. And if it were really this easy, computer vision would be a solved problem, right? We wouldn't have lots and lots of papers on this all the time. It turns out this is going to fail very hard. Okay, so you have to do something like this. But this thing again seems pretty complicated. So but really the only difference between this and sort of the textbook standard machine learning pipeline I showed you earlier with feature extraction is that my feature extractor is now a little bit more complicated. And so each of the boxes in this feature extractor is actually pretty understandable. And when you sort of assemble them together in the right way, you start to get something that you can understand yourself. So I'll start with just normalization, and I'm going to cover a few of the boxes. You know, image parsing we hopefully know how to do. It's just take a bunch of bytes and put them in an array in the right format. That's not that bad. Normalization, what is it? So we take our input images, which, as I said, are sort of pixel values from 0 to 255, and we now map them onto a new range. That's all it is. It's just a transformation of sort of the range of these pixels. And you could do fancier image normalization for sure, but that's the basic idea. And we do this because it makes the math work out a little bit easier later. So it turns out that if you want to compare two images for similarity, if they're on this range of -1 to +1, we can just sort of compare the pixels, multiply them together, and if the numbers are high, they're probably similar in value. If the numbers are low, they're probably dissimilar. This is also a necessary input to necessary pre-processing step for whitening, which I won't talk about today too much. The next thing is this idea of patch extraction. And you'll notice that in the diagram, it's kind of off to the side from the main feature extractor. It's because we do something sort of once up front, and then when we go to apply these things, we sort of have this patch extraction already done. But you can think of it as part of feature extraction as well. So what is patch extraction? Why are we doing this? So the idea is that we're trying to match pictures to sort of what's in them, right? And so one way to do that is to extract what we call a visual vocabulary. And so this is like little subset of the image, and usually these patches are much smaller than what I'm showing you, but basically it's things that look kind of like a tailpipe or a seat of the motorcycle or you know a rear view mirror, something like that, right? And so the intuition behind why we might want to do this comes from text processing, text classification. So if I'm trying to match documents as sports, I might look for words that are representative of sports, words like football or batter or whatever. Similarly, in image processing, if I'm trying to classify pictures as a face, I'm looking for things that look like an ear or an eye or a nose. In the motorcycle case, I'm looking for things that look like a rear view mirror or sort of or maybe a windshield. Okay? So that's patch extraction. That's why we're going to be using patch extraction. And convolution is the way that we match these patches to sort of what's in the normalized image. So convolutions are kind of this magical thing. They take what's called a filter or a convolution patch, and they walk across our image and apply sort of a sliding transformation to that image based on what's in the convolution. So it's really just sort of a weighted sum of the product of what's in the convolution window and the current window in the image. But what they enable is if you apply just a different convolution matrix to an image, you get a very different image on the right-hand side. So this is sort of the original image. I can do things like edge detection. I can do things like blur and filter. And so that's kind of interesting. And so what happens is if I apply maybe the windshield convolution to my picture of my motorcycle, I get only the pieces that look like the windshield that come out of the thing. And so what we're going to do is we're going to apply one of these convolutions for each of the words in our visual vocabulary. So each of the patches that we extracted in the last step will be applied to my input image. And now instead of just having one of these output images, I'm going to have as many as I have words in my visual vocabulary. So my input has now blown up from sort of one image to call it 1,000 images. And so I'm going to have many of these, 1,000 of these filtered images stacked next to each other. Okay, so the next step is this thing called symmetric rectification. It sounds really scary, but I included it as to explain what's going on here. So what does it actually do? It takes my numbers and it removes some noise. So I've got a bunch of numbers in a matrix up here, and if I apply symmetric rectification, given some alpha, some mask, all I'm going to do is take the max of what's in the image minus alpha and 0. What does that do? It removes noise. It takes numbers that are sort of uninteresting, values that are too low, and eliminates them from my input data. And that's pretty much it. So the last step of feature extraction is pooling. So pooling is the process, again, remember I have 1,000 of these filtered images. If I want to fit a model to 1,000 images, remember, 1,000 images is, and that's just a single data point that I care about. That's like, I don't know, 10,000, 100,000 kind of numbers. So what if we could take this and reduce dimensionality somehow? So pooling says, let's block up my image into quadrants. And you can imagine doing this a lot of different ways, but quadrants is one way that people seem to like. And sum up the values in my quadrants. And so reduce the sort of size of this multi-thousand single image, sort of number single image, just down to 4 numbers. And literally 4 numbers is what we're going to use in the pipelines today. 4 numbers per image. So now I've gone from 100,000 or more kind of numbers to represent my single input image down to, say, 4,000. And so if I sum up these activations in this quadrant, maybe in the top right quadrant I've got a much larger number, and in the lower, if it's all black, it's 0. Okay. So then the last step, now I've done my featurization, now I do linear classification. And this is the fancy machine learning model I'm using. And it turns out that this is one of the simplest machine learning models you can apply. And in this domain, it works surprisingly well. So I've got a data matrix. This is my A. I call it A. I've got some labels. This is the labeled images, which class they fall into. It's going to be, if I've got 1 million input images, maybe 1 million by 10. And then I've got my model. This X is what I want to learn. I'm mapping from my input data to this output labels. And the goal of the machine learning algorithm is to find the X which minimizes this error. And in this case, it'll be just like ordinary least squares error. So why linear classifiers? We know we have lots of fancier methods out there, right? We've got all these boosted things and whatever. So why do we use them? Well, they're simple, they're fast, and they're well studied. So Jim Demmel has 2 textbooks on solving linear systems, basically. They scale really well. We know how to scale them across a cluster. And with the right features, they actually do a really good job. So we put a little bit more effort into this featurization, and we can use a much simpler machine learning model at the end. And so getting back to our problem, let's say I'm trying to train on this ImageNet data set. And what is the size of this A and the X and the B in our model? So in the ImageNet case, this might be 10 million images down to 100,000 features. And 100,000 is maybe what you need to use to make this thing really work on sort of general natural images. Our model then is this 100,000 by 1K kind of representation of our data. That's our map. And then our training labels are similarly 10 million by 1,000. And this is actually something that's pretty easy to do if the number of features is small. And if the number of features gets up to 100,000 or so, we have to start being a little bit clever. And we're using a method called block coordinate descent, which works really well on Spark. But the point is that we can scale up this linear solver pretty well. So today's exercise, what you're going to do is build 3 image classification pipelines, a simple one, an intermediate one, and an advanced one. And then qualitatively, that is with your eyes, you're going to look at some of the output of these models. So how well do they classify a sample of input images? And also quantitatively, looking at the statistics of how the models work, compare their effectiveness. To summarize, the ML Pipelines project is about building reusable general purpose components that fit together well and are built with distributed data in mind from day one to put together complex systems for machine learning training and evaluation made up of well understood parts. So hopefully you can understand what each of these boxes is and compose your system that way. So that's it for me. I'm happy to take any questions. Yep.
How do you handle rotation of image features? I assume you can recognize regardless of the rotational.
Yeah. So the question is, how do we handle rotations? So that's actually a pretty good question. So there's a few ways you can handle that, right? You could either take in your sort of patch extraction phase, you could take a bunch of patches and sort of rotate them to handle that, and then you'll match regardless of the rotation. Or you can just start extracting more and more patches, blow up sort of the dimensionality of your model, and eventually you're probably going to find a patch that's sort of the rotated version of the rear view mirror, and so on. And so it turns out that if you just throw more features at this thing, they seem to start working better and better. That's sort of the surprising empirical result. Yeah.
How about
Oh, yeah. So the question is about our featureization method. Do we have any feature selection embedded in the pipeline? So right now, we're using regularization, which is a way to penalize the model and encourage sparsity. So that's sort of the featureization, the feature selection we use by default. It wouldn't be too hard to add something like stepwise regression or something like that to do feature selection for you as well. Maybe one more?
With regards to ML matrix, are you using Scala pack class in any way, or are you doing the same thing?
So the question is, with regards to ML matrix, are we using Scala pack or BLAS in any way? So we are using BLAS under the covers. I think we're using OpenBLAS, but it works with Atlas and so on. And we are, the communication patterns between the nodes are all encoded in sort of in Spark. So we have aggregation trees and that sort of thing to handle efficient shipping around of the blocks and the results.
Great. Let's thank our speaker.